Okay, so today we are pretty much going over the quantum numbers that I discussed last week. And this is pretty much the last part in chapter 2, the quantum mechanical model. So I wrote on all of this last week, so I'm trying to erase this so I can go ahead and go over the quantum numbers again. So I will start with the first quantum number that has the symbol N, the principal quantum number. And then once we go through this, you will see how this applies to the lab that's actually due this past week. Oh, hold on a second. What is going on? Oh, I apologize. That's my brother. I think he forgot I'm in class. But yeah, we will go over the quantum numbers and how it applies to the shapes. Okay. Remember, the first three quantum numbers essentially code to a specific shape, or what we call the orbital, where you find the electron. And then you have the last quantum number that actually codes to the spin of the electron. Once you find the electron in the orbital, you're trying to figure out what spin it has. The last quantum number, the m sub s, provides that information, right? Either the clockwise spin or the anti-clockwise spin, or counterclockwise spin, okay? So let me go back here and start. We went over this last week. I know we didn't meet on Wednesday, because school was out. We're not supposed to have any classes. So I won't erase all of this. I'll just go over it. We started off last week with the 4 quantum numbers, right? In the quantum mechanical model deals with those parameters, the 4 quantum numbers. So I'm going to write here summary. The quantum mechanical model provides us with 4 quantum numbers. Okay, so before we get into the quantum mechanical model, what we can actually look at is where we came from before we got to the quantum mechanical model. So right before the quantum mechanical model, what we had was Bohr's model. And Bohr's model was successful because Bohr's model really actually works for hydrogen. Bohr's model is the model where you have electrons moving around the nucleus in orbits. And the lab that was due this weekend, the one where you have to draw the planetary model, that is Bohr's model. Okay. Before we had Bohr's model, starting from the beginning, we started with Dalton's model, and his model was very simple. Dalton talked about the atom being round and there being no subatomic particle. After Dalton, we had J.J. Thomson. So I'm just kind of going back in time. J.J. Thomson was the scientist who discovered that there were subatomic particles. There were electrons inside the atom. So he had the plum pudding model, right? And his model talks about the atom being round, and you have electrons dispersed throughout like plums in the plum pudding model. And then JJ had his student slash friend, Rutherford, and Rutherford had the nuclear model. Okay, a nuclear model is similar to Bohr's model, only the nuclear model focused on the nucleus, ergo the name, the nuclear model, where the nucleus was finally discovered, and then the rest of the atom was vaguely discussed, but the rest of the atom was mostly empty space because the electrons do not occupy that much space, right? So the electrons are here. The nucleus is the one that's heavy. The nucleus is the one that's positive. His model focused on the nucleus and its discovery. Okay, so we have Dalton, we have JJ, we have Rutherford, we have Bohr's model. Then finally, we have the quantum mechanical model. Of all the preceding models, the quantum mechanical model looks the most like Bohr's model because it's a step above Bohr's model, right? Now, remember Bohr's model, the scientist Bohr saw electrons in orbit. So if we're going to do a compare contrast kind of thing, I'll write Bohr here on the left and what he saw. And the quantum mechanical model is not credited to one scientist because there are many scientists that came together to actually put that model together. So it's just called the quantum mechanical model, not assigned to one scientist. Okay, so yes, Bohr noticed that the electrons do have wave properties. He noticed that, right? Electrons were able to give off light. But the biggest thing he noticed was that electrons had specific orbits. Okay, and these orbits were like paths. They were like highways where you find the electrons. So imagine you were on a highway and you were driving on a highway, and it's kind of a weird sci-fi situation where you were stuck on that highway and you really couldn't go a lot of places just because it's a weird sci-fi situation, and you were in your car driving on a highway. That would be similar to the electron traveling on the orbit. Okay, so something amazing had to happen to allow the electron to leave the orbit we normally found it on for it to go to a neighboring orbit or a different orbit. Electrons could only travel from one orbit to another, and they did so by gaining energy or losing energy, because essentially Bohr said the orbit had energy, the electron had energy, and the energies had to match, right? So here we see electron and orbit energy, I should say energies, match. So if the electron is going to be on an orbit, we can assume the electron has energy that matches the orbit it's on. Okay? In the quantum mechanical model, we're told here that the electrons were found in orbitals. Okay, so the orbital is a little bigger than the orbit. The orbit is 2D because it's a path, but the orbital is 3D. It's like a bubble, a space, a balloon, or a house. Okay, a region where you find the electron. So now it's not a road anymore, but it's a whole space. Okay, the electron can be up, down, left, right within that region that scientists saw it. Now, the electron is still moving around the nucleus. They both agree on that. We see here that electron and orbital energies match. Okay, both Bohr model and quantum mechanical model agree that if the electron is found in an orbit, according to Bohr, or orbital, according to the quantum mechanical model, then the electron and the orbital energy match. So I'm saying this now because I really struggled with comprehending the textbook when I was a student. And we used British textbooks, which were written more, I would say, more complicated than the textbooks they have here. As in, they will keep flipping back and forth between electron energy and orbital energy. I didn't realize at first they were the same. So the author will be talking about the electron energy, but then he'll flip and say orbit energy or orbital energy. And I'm like, wait, so which is it? Electron or orbital? Because they're the same, they can flip back and forth. So if you're reading that and you come across that, don't spend too much time trying to decode that. Electron energy is orbital energy. Sometimes they'll be talking about something changing in the orbital when they mean something is changing with the electron. So essentially, where the electron is where the orbital is. The orbital is like the home that houses the electron, if that makes sense. Okay. Okay. So when we go into the quantum number, before we get into this, the other thing I want to talk about is, as we look back, Bohr discovered only one shape. And remember, his shape was 2D. So Bohr discovered the round orbit. Okay? And remember, the path where the electron was around the nucleus was round according to Bohr. With the quantum mechanical model, that group of scientists discovered that there wasn't just a round shape. So I'm going to draw the picture here so we can have a visual. This is what Bohr saw, right? So to kind of provide a more complete visual, based on what he saw, he drew his planetary model. And if you've done the lab, you've worked on this part here, right? You have the nucleus, you have energy level 1, energy level 2, energy level 3, energy level 4, and he labeled the energy levels as N. So N is 1 is energy level 1, N is 2, energy level 2, N is 3, energy level 3, N is 4, and it goes on and on and on. And we call this, of course, this is a nucleus right here, nucleus. We call this the planetary model because it does remind us of the sun and planets relationship, right? So this is Bohr's planetary model. So how do we reconcile what Bohr saw based on his experiments and then the quantum mechanical model? So according to the quantum mechanical model, they discovered, yeah, we have orbitals that have 3D. And these orbitals, depending on where the electron is located relative to the nucleus, are not just one shape. They're actually kind of categorized into 4 different groups of shapes. So they saw the round one, only the round one they saw was a sphere, right? They saw the one that looks like 2 spheres stuck together, the one that we call the figure 8, like that, okay? And they call this figure 8, or some books call it dumbbell. Okay, then the other one that looks like 4 spheres stuck together. So that would be 1, 2, 3, 4. Okay, anyway, you get the idea, right? This is called clover leaf. And it looks like 4 spheres stuck together. And then, of course, they saw the last one. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Yeah, I try to draw it like that, but y'all see in the picture, right? This is actually 8 circles stuck together, and I call this the flower because it looks like a flower. These are like petals of the flower. Okay. So you can see what they saw was multiples of what Bohr saw. Now, why did Bohr just see a simplistic view of what's actually happening? Technology makes a difference in the discovery in science. Bohr's time was way before the quantum mechanical model group of scientists, right? So this is all he was able to see. He was able to see the spherical shape. He didn't even see it as a sphere. He saw it as 2D, right? And it was limited, but he saw this over and over again, which is why they say that his model works best with hydrogen. So why hydrogen? Even though it has so many energy levels, right? Why hydrogen? Because hydrogen is the element that has 1 electron, and the 1 electron tends to occupy, the first electron in the atom tends to occupy an orbital that is round shaped or spherical shaped. So his model, though it has many orbits, only works for hydrogen. So when I say works best, technically only works for with hydrogen. So if you're ever asked what is the limitation, what is the issue with Bohr's planetary model, it is that his model only works for hydrogen. And then he also suggested that apparently when this electron is going around these orbits, it's constantly releasing energy. So scientists say, okay, well, if it keeps releasing energy, it will lose energy each time it releases energy, and it will move closer to the nucleus. One day, the electron would just implode into the nucleus, and then the atom will cease to exist. So then how come things are still around? So they said there were still cracks in the model, and that's why we now have the quantum mechanical model. Now, disclaimer, the quantum mechanical model is not perfect. We just haven't had enough data to produce a new model, right? Yay. That means the textbooks are not changing that much. Most of the stuff that we're learning right now is not that much new information. Okay. Does anybody have any questions? Let me make sure I go to the message box just in case. Y'all know if you have any questions, feel free to type it right here. Okay. Okay, so we're moving on. And so now that we know there's more than one shape, when it came to Bohr's model, there was no need for us to figure out, well, which shape the electron is in, because we knew the electrons were pretty much in the same shape, the same orbit, right? Just the question was, is it in orbit 1, orbit 2, orbit 3, orbit 4, 5, 6, 7, 8, 9, 10. But when we come to the quantum mechanical model, the 4 quantum numbers we deal with, and I talked about this last week, the 4 quantum numbers help us to get information. The first one is N, has a symbol N, or the letter N. Second one L. Third one M sub L. Fourth one M sub S. The N number, this is the summary of what we did last week. It's called the energy level. As I mentioned last week, it's also the formal term is principal quantum number. And the scientists got this number from Bohr. Okay. The other success that Bohr had was he was able to explain where light comes from in the atoms. He was also able to say that electrons have different energy level depending on what electron you're looking at. So N provides us with the energy level information. The energy level of the orbital or the electron. Remember, those two are interchangeable, right? And then L kind of gives you the generalized shape. General shape. Remember, we saw up here that with Bohr's model, there's really one shape, so you don't have to classify it. His was flat and it was circular. With the quantum mechanical model, though, there are 4 shapes. Which one is it? Is it sphere? Is it figure 8? Is it clover leaf? Or is it the flower? So L will help us specify that. Okay? M sub L. So when we combine these two, we get something called the sublevel. And the sublevel specifies both the energy level and the general shape. So you can say, okay, the electron is an energy level 1, but it has a shape of S. So if you've seen something like 1s, this is an example of a sublevel that combines both the energy level and the general shape. Okay? And so we'll be looking at things like that. If you've had electronic configurations in high school, this is where that information came from. Once we understand the foundation information, we can then use that to look at how electrons are sorted out within the atom. M sub L, this provides you with a specific orientation of the shapes. So we find that in the 4 main category of the different shapes, some of them are different in their orientation, where they are aligned in space. Some of them are different just because the whole shape is completely different. So here, I like to call this the specific shape or specific orientation. We get more specialized, we get more specific as we deal with the shape of the orbitals, okay? Remember, I told you once again, these 3 numbers here. So let me add one more page here. So in summary, before we go into and look, because I've talked about this before, right? When we look at N, L, and M sub L, these together, these 3 quantum numbers help us specify the orbit of the orbital, oh, I keep forgetting, orbital of the electron. Okay, so I taught this one time in a non-majors class, and I was telling them when we're trying to find the orbital of the electron or the electron itself, this is what we use, and we use these numbers kind of like GPS coordinates to locate your car, set of keys, your phone, my iPhone or whatever, find my whatever phone you have. We use these 3 quantum numbers to the orbital of the electron. Now remember, the orbital is it's a region. Imagine, you know, right now I'm looking. I bought something last week, and because of the bad weather, it's taken a while to get here. So you know what I did? I kind of used GPS location to find out exactly where my package is. And they were able to tell me, it's coming from Florida. So they told me exactly where it is right now, right? So you can use that GPS coordinate packages and they give you a tracking number. So at least we're familiar with using coordinates to locate things, right? We're going to be using these coordinates here, the 4 quantum numbers, first 3, to locate the orbital of the electron. Remember that, okay? Now, the last one, M sub S, it does not help us find the electron. Once we find the electron, it helps us specify the spin. The two options here are spin, and then the other one is counterclockwise. Okay, have those two options. Okay, now that I decoding that, let's go ahead and see what we discussed last week so we can get to the end of the chapter. We talked about this last week, and once again, it's the energy level. I won't go over all this again because I already went over it last week. Just to say that make sure you know N characterizes the energy level of the orbital. They got this from Bohr. Make sure you know the restriction. I mentioned earlier that, hold on a second. Let me pull up my other sheet that I had here earlier. Okay, should be somewhere here. Oh yeah, your lab. I would like for you guys to work on this lab before you do the exam because it will be helpful. In your lab that is due this weekend, I know it's due this weekend, but I couldn't fit it anywhere else. You can work on question number 1, find that out in the PowerPoint for chapter 3. But for number 2, this summarizes the 4 quantum numbers, as you can see right here. Okay? And so it tells you, well, you have to provide the official name. You can provide the official name and then the casual name in the name part. So for example, since we're here, let me show you how to draw. I've forgotten, man. Okay, so for this first one, I can write here principal. Okay, hold on, sorry. Let me see. Oh, at the end of the session? Okay. Wait, you're talking about this lab right here? Jennifer? Jennifer, are you talking about the lab I'm going over right now or a different lab? Are you saying, can I move to the other session? Is that what you're asking?
I wanted to talk about the last lab that we were supposed to work on.
This one here?
No, the other one from chapter 2.
Oh, the one with the planetary model?
Yeah.
Oh, okay. I see what you're saying. So you're not asking me to move it to the back. I see. Okay. So let me be clear. You're talking about the one with the Bohr's model, right? Let me go back here. This one?
Yeah.
Okay. I know there's a lot of clutter here. I do have actually a video posted here on that one. I don't know if you got to that video. I should write here video. There's a video on going over that one, but since you asked, let me go over that one first because that one does have to do with the old model. So it'd be confusing to go over it after we're done with the new model. So let me just skim over that real quick. But yeah, this one here is talking about Bohr's model, right? So that's what we just covered. So I gave you guys some examples of how to work this out. Remember, Bohr's model, the planetary model, it only works for hydrogen. So they tell you all the stuff here about it. And this model is based on once you get some hydrogen, you're trying to figure out what kind of, well, where the electrons are, what energy level. Remember I told you with Bohr's model, we don't have different shapes. We just have the same shape over and over again. Like the Russian dolls, you have a circle inside a circle and it gets bigger and bigger and bigger and bigger, right? So towards the end here, let me zoom this out a little bit. Towards the end of the model right here, I do that. This is essentially Bohr's planetary model. So we're trying to see, essentially we're being told in Bohr's planetary model, there's so many different transitions that actually take place, right? But we're trying to figure out which ones that we actually experience in the lab. So before I go any more into that, I have to go back to this right here. Excuse the many pages that I have. So in the lab, what would have happened is you would have seen something like this. We have a spectral tube, and the tube will be releasing light. The gas in here will be hydrogen, and then you'll be asked to see what kind of band lights that you see. Okay. Remember, this is called the line spectrum. We're not seeing the full spectrum starting from, Roy, G, all the way to big. We're not seeing all the bands kind of blend into each other like a tie-dye. We're only seeing specific lines, and that's what they call this the line spectrum. Remember, each element has its own pattern of line spectra. We're looking at hydrogen right now. This is just for hydrogen. So in the lab, if you were watching this using a spectroscope, you will see 4 bands from hydrogen. So these 4 bands, whenever they're present, they communicate to you, you are looking at hydrogen. Okay, so I have this picture right here. There is a video about it right here just to show you what the emission spectra is for Bohr's model. So there's a picture, there's a video, and there's another video here too. Okay, so once you've seen that, we're going through the work in your lab that was due this weekend to figure out how you get the force. They tell you each color essentially goes with a wavelength. So you have that. So red goes with this wavelength. You have to get the remaining of this. So to get the blue-green wavelength, it says these come from your. Actually, when I said the textbook, oh, this is not the actual lab instruction. If you look at the actual lab instruction, the directions were on there where it shows you the wavelengths for blue, green, blue, violet, and violet. Or even if you look at this picture right here, it tells you the wavelengths, right? These are the wavelengths for the different colors. So I had here red 656.2. That's this number right here. You can find blue, green, you can find blue, violet, you can find violet. Okay, and that will help you fill these up. Then when you're done, oops, when you're done, I show you how to get the frequency and what your answer should be for your first one. So don't just go ahead and work the second one and the third and the fourth. Make sure you work the first one so you get your answer to match mine. Many times y'all forget to use parentheses with your scientific notation. So I put this here and I tell you, make sure you work it out so you have the magnitude of 10 power 14. If you do get the first one right, use the same method to get the other 3. Okay? And I tell you what to do with step 3A. So this is not the lab form that you have to fill. This is the help one. That's why I have all these notes on here. So some of you go ahead and fill this one and turn it in. I don't mind that as long as the notes I have here does not obscure your answers. If it obscures your answers, I can't see your answers, and I'm grading your work, not my work, right? So make sure if you use, like this one here, it blocks what's behind. So if you're going to use it, make sure this notes is gone. But anyway, I show you here how to calculate RH over H. I tell you what RH is. All this dialogue is in your lab instructions. People struggle to find the information. I guess they get bored reading it. So I have it written out here for you. What is RH? It's a constant, and it's provided this number right here. What is H? Another constant is provided right here. This is the Rydberg's constant. Please read the actual lab instructions and then make sure you're getting this information, because the goal is for you to know how to read the material versus just completing the lab, right? Because at some point you need to know how to get this information from the lab. And then, yeah, once you take RH, divide by H, you get this number right here. Make sure you get this number. Once again, plug in your calculator. And then this number is the same throughout. This number right here is going to be different because your Ni and your Nf values are different each time. So you have 1 over Ni squared. This is Ni. 1 over Nf squared. This is Nf. So you're going to take those numbers, and then let me write it out here real quick. For the first one, it's going to be 1 over 1 squared minus 1 over 2 squared, right? And when you work this out, you get it in decimal form, 0.75. In the end, you multiply these two numbers and you get that. Do that for all of these. Do that for all of these. And then make sure you write your numbers in the proper scientific form. Don't write a number here that's the base number that's less than 1, it has to be in the proper scientific form, and then that way it will work out. Then once you get all of these possible transitions of the electrons, these are all the electronic movements happening in the hydrogen atoms, you're going to find this is supposedly your experiment, data table 2. This is showing you all the possible transitions happening right now as we speak in the hydrogen atom. There's an electron going from energy level 2 to 1 or 1 to 2, vice versa, right? 1 to 3 or 3 to 1, 1 to 4 or 4 to 1. So the electrons are moving all over the place, and these are the allowed movements from the different energy levels. So the question is, once you get the frequency from this last column, the theoretical frequency, and then the one you got from your experiment, you only got 4 in the experiment. So the 4 you got in the experiment have to match 4 from all the available, hold on, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12 possible transitions, right? Producing 12 possible frequencies. Of the 12, 4 here will match, will be very close to the 4 that you have right here. So figure out which 4. Once you figure out which 4, so I do have a video of this already explained and recorded there. You probably need to look through the link. Don't lose heart. Click through all those links. It's important to help you because I've already explained all this stuff if you want to look at that again. Once you figure out which 4 from here, so say, for example, you say that this one here matches one of the ones we have here. So I'm just making this up, right? Let's say the second one is 2.47 times 10 power 15. Then I can say, oh, this one here matches this. Then when it comes to this page right here, that went with a red color, right? They say compare data table 3 with 2. And then, oh, sorry, that goes with the blue-green color. So the blue-green color that we have here matches the one I have, oops, down here. You see that, right? It matches this. So from 1 to 2, that will work for my blue-green color, right here, NF, and Ni1, NF2. So the electron that produces the blue-green color moves between Ni being 1 and NF being 2. So we see the blue-green color when the electron is going from energy level 2 to 1. Okay, you will end up having 4 different sets of transitions of the electron as it goes from this state, the ground state, to the excited state. Once you're done with these 4, you will then draw this. You want to make sure you label this. So this is N equal 1, N is 2, N is 3, N is 4. Remember, this is Bohr's model, right? So all we're seeing here is circle. And then here we have our nucleus in the middle. And to show you the blue-green, let me use a blue-green color. Let's make that the blue-green color. My electron for this one here is going from 2 to 1, right? So I'm going to draw this going from, this is 2 to 1. This is too thick, but you get the idea, right? The electron is going from here to produce the color. So you have to end up drawing 4 different transitions, and then that's the end. Does that answer your question? Okay. Did that answer your question, Jennifer?
Yes.
Okay. Yeah, so that pretty much wraps up Bohr's model, right? Remember, his model was all about the planetary, the electrons moving up and down. So now that we're back to this new lab, which now talks about the 4 quantum numbers, your first one here you will write. So to answer this, you have to kind of go with your PowerPoint. First one here, oops, let me move over here. Principal quantum number, N. You write that, principal quantum number. I'm going to write this in shorthand, just to help you fill out the first. Symbol N, you put here N. Restrictions, okay, you go through here. It tells you N can be any whole number, integer greater than 1. So you can write here N. I mean, the better you write, the easier it is for you to review. Because in the end, these labs become useful resource for you to review, right? You can write it like this if it makes sense to you, or you can write here, n is a whole number. Some people write n is equal to 1, 2, 3, all the way to infinity. Write it in a way that it's accurate, but it makes sense to you, right? We have our first quantum number, principal quantum number, symbol n. Okay, information the quantum number provides. Okay, we know that it provides the energy level. So you can write that here. It provides energy level of the of electron and orbital. Excuse my handwriting, I'm writing with my mouse. Okay, and you can write as much information as you want because this is ultimately supposed to be helpful for you. Yeah, so that's kind of how this ties in back and forth. So I'll be going back and forth between the lecture and the lab because they do tie in, right? So you would do that for all the 4 quantum numbers as you go through, right? You do the principal quantum number. This is a review from last week. You know what it provides. And it tells you here what's important for you to remember. The principal quantum number, like we saw in your lab, the energy level, it provides you the energy level of the electron or the orbital. It tells you how close or how far the electron is to the nucleus. So you can write information as you need because ultimately you're doing the lab, going over the lecture, and then of course reviewing the information. Symbol is this. As I said last week, you can write this the restriction as it has to be a whole number. It cannot be fractional, right? So you can start with n greater than or equal to 1, or means n1, n is 2, n is 3, 4, 5, all the way to infinity. Okay? Now, when you do this for all the quantum numbers, that helps you complete the table. Now, I discussed all of this last week, and then I want to get to this part right here because I do want to finish this chapter today because I already did all this last week. So, here's the thing that I want to review as we go over this part. The periodic table helps us to apply the quantum numbers, right? To figure out what the 3 quantum numbers are for the element. So you want to be able to do, given the element, you want to be able to provide the 3 quantum numbers, or vice versa. Given the 3 quantum numbers, you want to be able to figure out what elements they are, okay? So right here, I have these written here. I gave them different numbers because, sorry, different colors because of the different groups. Remember, we group things to make it easier for us to learn. So please notice as I'm working on this, the red group right here, since we have talked about this before, I can actually be more holistic about this. The red group, this is all the S block elements. Remember last week I mentioned S block, these are the round ones, the spherical ones. Spherical. Okay, so you have in this block right here, so I like to call it the block, a neighborhood block. In this block right here, you have a spherical ones. The spherical, the round in energy level 1 tends to be really small. As we get to energy level 2, it gets bigger because just like Bohr's model here, where we have the concentric circles, the orbitals are inside each other. The small ones are inside the really, really big ones, right? So kind of like this, only Bohr's model, this model here was 2D, and in the quantum mechanical model, this model here is 3D. So you have a small sphere, a big sphere, an even bigger sphere, and the sphere keeps getting bigger as you go down the energy level, bigger, 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 and then very big, right? Tiny sphere, bigger sphere, bigger sphere. So you need to know the energy level. So let me erase that so you can see the energy level. N1, N2, N3, N4, N5, N6, N7. And remember, these elements here, you want to make sure you have this written down as you're reviewing your notes for the energy levels in the periodic table, okay? This will be classified as energy level 1, 2, 3, 4, 5, 6, 7. Now that I'm done with the S block, remember all of these orbitals here, the orbitals are called S orbitals. They're all round, right? Or spherical. And these are the energy levels. Now we're moving on to the p orbitals. The blue part is the next part. This is the group of p orbitals. In the p orbitals, remember the p orbitals, they're the ones that have the figure 8. With the p orbitals, we don't start up, there's no p orbital in energy level 1. So the p orbital starts off at the next energy level 2, 3, 4, 5, 6, 7. So make sure you understand that in the p block, or in the region where the p orbital is, we're starting from energy level 2, 2, 3, 4, 5, 6, 7. Okay? You want to make sure you really understand this part, because we're going to be doing some more complicated stuff with this. So don't skim over this chapter or this section here because it's a little complicated. Okay, so N2, 3, 4, 5, 6, 7. And then this is called the p orbital. Generic shape, remember, it's figure 8. So figure 8. And then here in the pink section, this is called the d orbital. With the pink section here, d orbital, this is actually the general shape of the clover leaf right here, like that. Right? So with the d orbital, you can see here, this starts off, there's no d orbital energy level 1 or 2. The scientists didn't find any. The d orbital starts with energy level 3. So realize S starts with 1, P starts with 2, D starts with 3. N is 3, N is 4, N is 5, N is 6. This is as far as it goes. Then finally down here, I meet the F orbital, the flower orbital. With the F orbital, that's shaped like a flower, F orbital, scientists didn't find any in energy level 1, 2, 3. They finally found it in 4. Okay? So in this weird assignment of orbitals or energy levels for the different orbitals, notice sequentially it increases like this. And this starts from n is 1 all the way to n is 7. This starts from n is 2. This starts from n is 3. This starts from n is 4. So make sure you remember that. Okay, so the F orbital, the flower orbital, is not seen in energy level 1, 2, 3, but we begin to see it energy level 4. Okay, we talked about the angular momentum last week, and I mentioned to you how the angular momentum, the values here, so you go back, right, to the lab, and then you write the angular momentum. Symbol here is L. Angular momentum starts from, the symbol is L. It starts from 0 all the way to, what's n minus 1? Oh, n minus 1. So this would be your restriction right here. It can never, L value can never be equal to n value. It will always be 1 less. Okay? And we got to practice some of this last week, where we said the s orbitals tend to have an L value equals 0. P orbitals have an L value equal 1. D orbital have an L value equal 2. F orbital have an L value equal 3. Okay? So here, I don't think I had a periodic table right here with me, but I did go through this with you guys last week, and I mentioned that, of course, spherical orbital has s orbital right here. So what I want to do right now is combine these, because my goal is to finish the chapters. Combine these as we look at the periodic table. Let me see if I can pull one from right here real quick. Periodic table. Let me see if I can see one that's not too bad to work with. It's hard to get good periodic tables these days. Okay, let me see. I'm trying to copy. Let me see if I can get it into my app. So we can see the elements, right? We can actually work on that. Add a page on the bottom here. Oh no, it's not bringing the periodic table. Oh. Yeah, it added a page. Let me try it again. Copy. I refuse to pay money for that. Okay, copy, go over here, add a page. Will it not let me paste image? Oh, okay. Ah, they changed the app. Okay, sorry about that. I forget they changed the app, so the method that you go from to accomplish things, before I just tapped it and it allowed me. Okay, so having this very fuzzy looking, I do apologize for that. Man, it's grainy and fuzzy looking periodic table. Okay, I want us to go ahead and classify this. So real quick, remember, helium for this purpose is a roommate of hydrogen. So you want to move it over here. So one of the questions in your lab has you actually, where is that lab? Down here. Has you join the periodic table, a mock, right? And then you have to go through and actually, yeah, outline the periodic table, and as well as label the different areas corresponding to the filling of the S, P, D, and F electron. So what I'm doing right now is similar to what they're asking you to do for number 4. Okay, I'm actually outlining my periodic table. So you would have to do that. You don't have to use a real periodic table. You can just use something that you can just draw it out. Okay, so for number 4, I'm going to outline. I'll start with this one here. This block I am blocking out in the periodic table. All these elements here, their last electron is in the s orbital. Okay, and I'm going to use a different color for P. This right here. Except for helium, these are all p orbital electrons. Now they haven't asked me for energy level, right? Then when I move down here, these are all technically d orbitals. Then I finally have my f orbitals. Right there. Okay, so essentially, if you want to leave this up here, it's okay. You just have to make sure that the color here, oops, it has to be red, matches, yeah, the helium matches the rest of it. Okay, now they're asking for energy level. I'm going to go through and use this one right here. Maybe, nah, I'm going to use the black one to write. Okay, so remember, this starts from, come on, okay, energy level. Ooh, that was too big. Smaller. N is 1, N is 2, N is 3, N is 4, right? We go through all this. So what I want to do is, based on what we did last week, I want to go ahead and assign the 3 different values. N, L, M sub L for platinum. Okay? So this is a quick review. We did this last week. N is 1, 2, 3, 4. N is 5, 6, 7. Here, N is 2, N is 2, N is 3, N is 4, N is 5, N is 6, N is 7. N is 3, N is 4, N is 5, N is 6, N is 4, N is 5. So each time for each block, I'm starting one lower for the N value, right? So for platinum, oh, I didn't label the L's. Okay, this is L. Oops. This is L. Oh, why won't it allow me to write? I'm not trying to do anything. Enable caption. I don't know what that is. Disable caption. Hold on. I pressed something by mistake. Okay. And okay, right there. L equals 0 for this whole thing. This is L equal here. L equal 1, L equal 2, L equal 3. Okay. And then last week we did the M sub L2, but for right now, let's see. For this whole column here, M sub L equals 0. We did this one here last week, which was negative 1, 0, 1. Okay. So it will actually be easy. As I'm looking at this right now, I'm thinking to myself, it'll be easier to use the periodic table I already have in here that we worked on last week. Okay. So let me write the symbols right here. So it's a lot easier. It's a lot cleaner. Platinum is all the way here. 1, 2, 3, 4. No, 1, 2, 3. 1, 2, 3. Platinum is right here. Okay, this needs to be a little finer. Yeah, platinum is right there. So to figure out the energy level for platinum, remember, this starts with N is 3, N is 4, N is 5, N is 6. So you can see for platinum, N is 3. And then, of course, this is L is 0, L is 1, L is 2, L is 3, L is 2 for platinum. And then the M sub L, you see it right here. M sub L is 1. Okay? So we discussed this last week. Now you won't write it this way. You just write the numbers as is because they'll be written in the order of N, L, M sub L. So you will write N is 5, L is 2, M sub L is 1, right? And then if you're looking for something that's, let's say this one right here, lutetium, Lu. For Lu, once again, this is N is equal to 4, N equal 5. So you start with, for Lu, in the order N, L, M sub L. N is, let's see, N is 4, based on this. L is 3, based on that. M sub L is 3, based on what I have up here. Okay, so you want to know how to read this. I'm reading this. This is M sub L. This is my L. And then this is my N, which I put in the labels myself. And this is essentially where we left off last week. I was just kind of getting us caught up. Last week, I remember skipping over this question. I want to make sure I answered that. So I'm just kind of going through and making sure I've covered everything I skipped over last week. It says here, what values, numerical or letter, of L are possible for N is 3? Okay, so they're asking you, find all your N is equal to 3, and what values of the letter L are possible. So what I do, because when I was working on this as a student, I felt like the questions were somewhat vague. And if you feel vagueness, what I did was I relied on the periodic table to help me answer this. So they're asking you, there's so many different values of L. Based on what we've seen right now, we have 4 different major shapes, right? So we have the L is 0 for the round one, L is 1 for the one that has 2 bubbles, L is 2, L is 3, right? But they're asking you, how many of these L's are possible when N is 3? That's how I read the question. Can we use all 3 of these? Or do we use just a couple of them? So let's go find in the periodic table where N is 3. Okay? So what I like to do is, we can use this one, I guess. Let's use this one here. It tends to be the cleanest because let me see, the other periodic table, this is a mess. We can use this one too, that will work. Okay, so what I'm going to do here, I'm going to highlight all the N is equal to 3, right? So in the S block, N starts at 1, N, 2, N is 3. So this is my first, N is 3 from the S block. From the P block, we start at N is 2, N is 3, and then this is as far as I'm going. I'm trying to find all my N is 3s, right? Because they're asking you how many different L's can you have for N is 3. Okay, I know when I get to the D block starts at N is 3. Oh, that's it. I don't have to go any further. That's another N is 3. It goes from here all the way to here. I know for my F block starts at N is 4. So F block technically doesn't have an N is 3, right? So I only see 3 areas in the periodic table, or 3 regions in the periodic table that have an N is 3. I have an N is 3 here. I have an N is 3 here. I have an N is 3 here. But what they asked you was, which L values correspond with N is 3? Well, I see an N is 3 when L is equal to 0, because remember this block here is called L is 0. I see another N is 3 when L is equal to 1. I see another n is 3 when L is equal to 2, right? Or you can use the letters. L is 0 or S block. L is 1 or P block. L is 2 or D block. So you can call it, they use either number or letter to answer that question, right? If you're working on your homework, you want to pick the answer that fits with the question they're asking you. There is no N is 3 in F. F starts at 4. It only has 4 and 5, right? For the N values. So that's why it's important to know that. When I was going to school, we didn't have the table like this. Man, I remember I'll just leave my comments to myself. Let's just say we didn't have the table. I was like, huh? How did you figure that out? Right. So we saw one for 0. So this all these apply. We saw one for 1. All these apply. We saw one for 2, but we didn't see one for 3. So our answer that fits is this one here. This one here doesn't fit because there is no n is equal to 3 in the F block. Right? There's n is 3 in S, P, oops, wrong thing. S, P, and D. Okay? You have to know how they ask questions. That means to be comfortable with the language of chemistry, you have to read a lot. Just like with any language, right? Or communicate in the language, use it a lot. So with the M sub L value, we talked about that. And as we're going through this here, I want to answer a couple of questions with your lab work once again because it ties in very well to this. So as we're going over magnetic quantum number, I went over this last week because I saw it somewhere, written somewhere here. I want to go over that, then we'll go over the periodic table, the magnetic spin, okay, in this context. So what I want to do right here is talk about the different energy levels and what's possible. Actually, I want to just stick with the L levels. So for the different L, we know we have an L that's 0, an L that's 1, an L that's 2, and an L that's 3. Remember, 0 goes with a circle, the 1 goes with a figure 8, right? So I'm sticking with the numbers for right now. These are generic shapes. Then the letters that go with these shapes are S, P, D, and F, right? Remember, S is round, 2 circles, 4 circles, 8 circles, okay? Now, what I'm doing here is showing you how we go from the L value, the letters that go with it, to the M sub L values, because over here we're told the M sub L values are actually derived from the L values. How do you get them? These are, again, whole numbers. They're integers that go from negative L. So you start with whatever your negative L value is, go all the way and end up on a positive L value, but you have to go through 0. Okay? So you start from negative L, add 1, add 1, add 1, stop at positive L. Okay? So we're going to be doing this part here to fill in our last column. When we start with L being 0, you have to start with negative L, go all the way to 0, and with positive L. So remember, M sub L is technically derived from L. So once we know what L is, we can figure out what the allowed values for M sub L is. So when L is 0, since we have to start and end with the value of L, right? This is only 0. When L is 0, M sub L is 0. Why? Because negative 0 is 0, positive 0 is 0, so that's it. M sub L is 0. Okay, this one here, the next one, when L is 1, we go like this, negative 1, comma, 0, comma, positive 1. So when L is 1, you write out negative 1 plus negative 1 first, add 1 to get to 0, add 1, you get to positive 1. So we end up with 3 different numbers assigned to M sub L when L is 1. Next one, when L is 2, we end up with 5 different numbers. What does that mean? You end up with negative 2, add 1, negative 1, add 1, 0, add 1, positive 1, add 1, positive 2. So you see how I'm obeying the format here. Start with negative, L, add 1 each time until you get to 0. Keep adding until you get to positive L. And that gets you here. -3, oops, I need the space. -3, add 1, -2, add 1. So I'm starting negative L, right? -1, add 1, 0, add 1, +1, add 1, +2, add 1, +3. You get at positive L, okay? So once we have all these numbers here, what do they mean? M sub L value, so each M sub L value codes to specific, not just a shape, specific orbital. So this would be like providing somebody your home address, and M sub L value is your home number. You know, they know what block you live on, they know what street you live on, but M sub L is your home number. So the M sub L codes to the specific home, aka orbital, of the electron. So with that, then let me see if I can minimize this shape a little bit. I'm trying to get used to, oops, trying to get used to this new thing that they did here. Oops. I don't know. I get that apps have to update and be all new and stuff. I just, once I figured out how to use it, I don't like to learn a new process. Y'all know what I mean. I'm like, why did you fix it? It wasn't broken. Can you add features without taking away features? Please. Okay, that's just me, my complaints. Y'all know. Okay, so right here, once we have this, what does it mean to us? As far as the number of shapes are concerned, we should expect just one shape there. Now remember, the shapes are essentially the orbitals, right? These are this, orbitals or shapes. It's going to be one. For p orbitals, we expect to have 3, because remember, each one of these codes to a specific shape or orbital. This one here, we should expect to have 5. This one here, 1, 2, 3, 4, 5, 6, 7, we should expect to have 7. Okay. Once again, my goal today was to translate this to match it up to your lab. So let's go ahead and detour from this page to your lab book or your lab handout, wherever it is. Okay, so I skipped over to number 4 because what I'm going to be doing next is number 3. So I'm going to go back to number 3. I'm not working everything out. I'm just trying to help you guys out with this one here. Okay, and relating your lecture to your lab work. Okay, this one here, it says, for various combination quantum numbers L, M sub L, and M sub S, enter the appropriate information in the following table. Oh, I just realized we haven't gone over M sub S. My bad. Let me go over M sub S and then we'll come back to that. So yeah, because we'll only be able to answer everything except for M sub S. So let me go ahead and finish that part out. We will come back to this page right here. Remember, this shows you the M sub L. Based on what we just covered, we just said there was only one M sub L for the S shape. That's it right here. M sub L is equal to 0. That applies to the first 2 columns. Like everything in the S block is M sub L 0. That just means these are all round, right? Spherical. In the P block, so I'm trying to make sure I go over this again. In the P block, there are 3 different kinds of P blocks, apparently, or P shapes. They are all the same shape, like this figure 8, but they have 3 different orientations. The M sub L equal -1 is usually P sub X. This is P sub Y, and this is P sub Z, PZ. So PX, PY, PZ. Well, how are these different? Okay. As far as the letters are concerned, remember, if they ask you for the number, you have to provide this number, -1, 0, +1. If they ask you for the letters, PX, PY, PZ, well, how do you know what is PX? How do you know what is PY? How do you know what is PZ? I know we're kind of just learning this as I'm remixing it, right? So here, when we go to PX, remember the S only has one shape. When we go to PX, PY, PZ, I just went over these numbers already. PX looks like this. Remember the axes. So we have axes here. In chemistry, the vertical one is Z, the horizontal one is X, and this one here is Y. So Px just shows you the P orbital with the x-axis going right through it like a shish kebab. Okay, so the the x-axis goes through the px orbital, and then the py orbital, the y-axis goes through it, ergo py. And then the pz orbital, that's the vertical one, the z-axis goes through it. Okay, so you want to be able to know px, py, pz. Okay, and you want to know how they are different. You want to know that there's only one S. So there's no S is just called S. There's no SX or SY or SZ because all the three axes go right through S. So there is only S and it's just called S. With P, there is PX, PY, PZ. This is -1, M sub L equals 0, M sub L equal +1. Okay? When it comes to the D gets a little complicated. We went over D when we discussed the M sub L, 2, -1, 0 plus 1 plus 2. We went over that already. So when it comes to the shape, realize that there are so many different letters that go with it here. This gets a little complicated, so I usually tell you the one you want to be aware of. Just be aware of what a D orbital looks like be able to identify. If you're given a picture and they ask you, is this a D orbital? You want to recognize the D orbital has got the 4 bubbles like that. This is D, this is D. These are all D's at different orientation. This one here, I call it the left to right orientation. It's like a TV screen that you're watching. This one here, yeah, the plane matches the screen that you are facing, right? So left to right orientation. This one here is lying on the table. So it's in front of you, but it's lying on the XY plane. The one that has the left to right orientation is lying on the YZ plane, not axis, a plane. Okay. This one that's kind of facing in and out is you are facing it perpendicular. So it's facing a different side from you, perpendicular to you. This is the DXZ orbital. Okay. This one looks just like that one, if you ask me. The only difference is for this one here, the orbitals, oops, like a shish kebab, go right through, the axes go right through the orbital here. While here, the bubbles are between the axes. So I would say just make sure you recognize what a d orbital looks like from the others. And then right here, you want to be able to draw this one. It's natural for them to ask you that because it's the most different of them all. It's a d orbital, right? But it looks like a p orbital. The difference here is it's a d orbital that has a little balloon on its waist. So it's a dz squared orbital. That's its name. It looks like, I'll say here, looks like pz, right? PZ was vertical and it had the 2 lobes. Only this has a little balloon thing or floaty thing on its waist. So recognize the d orbital. Make sure you know how to draw the dz squared orbital. Okay. You will not be asked to draw the F. So with the F, you want to just be familiar with it while we're here. Notice the F's, the different F's. Just be familiar. These are F's. They're complicated. They look more complicated than flowers, right? But that's the F orbitals. Okay. So now that we've seen this, actually, before I got to that table, I thought about something else, which is right here. Where is my lab? I thought about something else that I skipped over. Was it number 2? No. I think because periodic table. Oh, here, number 5. Okay. Number 5 says sketch or draw the shapes of all the various orbitals corresponding to L is 0, L is 1, L is 2. Okay, I just showed this to you, right? So for L is 0, when L is 0, we only have the S orbital. So for that one, you draw your axes. I'm just kind of going over this with you. Axes, that's going to be, what is this here? X, Y, and the Z is vertical. And you draw the circle in the middle, and this would be your S orbital. You only have one S. When L is equal to 1, remember, we have 3 M sub L's. So that means you're going to have P, right? You're going to have PX, you're going to have PY, and you're going to have PZs. So you have to draw all these P's, right? Remember, this is M sub L equal -1, M sub L equal 0, M sub L equal +1. So here, you draw your axes, you draw your axes, you draw your axes, and this is X, Y, Z, X, Y, Z. Woo, it's hard to draw. X, Y, Z, right? So for this one here, PX, this is X. Your P orbital lies in the X plane. PY, it has to lie. No, sorry, it has to lie on the y-axis, not plane. This time it's axes because it's just one letter, right? Then this PZ up and down. So you would draw this nicely on your lab, right? Remember, when L is 2, you have how many M sub L's? 5. So you should have 5 shapes. People just draw 1, and I'm like, what about the other ones? They're not representative ones. You're drawing all 5. So when L is equal to 2, for D, you're drawing 5 shapes. So, yeah, I say draw all 5 shapes. Don't worry too much about making sure the shapes lie on the plane. It's hard to draw something that's supposed to be 3D in 2D, right? So when I say draw all 5 shapes, what I mean, back to this one here, is, oh, we already drew that. Well, I try to draw that. You're going to be drawing these 5 shapes. Do your best. Do your best, okay? Just notice with these ones here, the bubbles show up between the axes, right? Here it's hard to show this. Just do your best. Do your best. This one here is between the axes. I mean, you can argue what I'm really showing. People say what I draw is literally the same thing. I'm like, don't even worry too much. But this one here, the DZ squared has to look like DZ squared. If it looks like one of the other ones, then of course it's obviously not correct, right? So you're doing this for, this is going to be your L is 2, right? This is going to be for your L is 1, and this is for L is 0. Okay, so we've answered another question in your lab. Okay, now I have to go over the final quantum number so we can finally answer that one question that I haven't done yet. I know I haven't done it yet. Okay, so in the final quantum number, once we get to the M sub L level, we're now in the orbital, right, inside the shape, the round or this. We're told that we have two electrons in there. Now, in the orbital, you have 3 possible positions. So I'm going to write this here. The orbital can be empty. It can have 1 electron, can have 2 electrons. Okay, so when you arrive at the orbital, I say house because house is more relatable. I realize not everybody, every student got to live in dorms. In the beginning, I used to say dorms, and I realized some people haven't gotten to be in dorms. If you were in dorms, this would make more sense. That if somebody were looking for you, use the 3 quantum numbers to find your dorm room. Usually in dorms, most dorms at least, you have per room 2 students, right? So if you arrive at that dorm, you're at the door, you open the door. The room can be empty, scenario 1. It can have 1 person in there or 1 electron, scenario 2, or it can be full, scenario 3. Okay? Now, this is not actually a room, it's an orbital. You can have 1 electron, 2 electrons, which is the max, or it can be empty. Okay? So we're now trying to describe which electron we're seeing, magnetic spin. The spin quantum number describes the spin behavior of the electron in the atomic orbital. So once we've gotten to that 3D space where the electron is, the spin tells us what electron. It specifies the orientation of the electrons in the orbital. Remember, when you're filling that second table in your lab, the restriction for this one here is positive 1/2, negative 1/2. You can only have two values. Positive 1/2 is the up spin. It's shown like that. The number is positive 1/2. Negative 1/2 is the down spin. Numerically, it's shown like this, or you draw it like that. Okay? So then I go back to the periodic table and show you how this part of the periodic table, we're only featuring and focusing on magnetic spin. Okay? And remember, the boxes here represent the elements. So we have hydrogen, we have helium, and then it goes on and on and on. So the last electron in hydrogen has an up spin. The last electron in helium has a down spin. And it goes from here. So up spin is positive 1/2, up arrow. The down spin or the down arrow is negative 1/2. So I have all of these information here for you to look over. So it always starts with up, down, up, down. The first one that's placed in the empty orbital is always up spin. And the electrons in the orbital have to always be opposite spin. It would be like, once again, this is not a dorm situation, but it would be like if it was a dorm situation, the rule is the dorm room can have a maximum of 2 people. It can be empty, it can have 1 person, and if it has 1 person, we all know it's half filled because the full capacity is 2 people, right? And the rule here is they have to have opposite genders. So if you have one gender first, the second one that comes in has to have opposite gender, and then that's kind of how it works. So this is how I was rationalizing as a student, because I was a student living that dorm life, trying to relate to this quantum stuff, and I'm like, I'm not feeling this quantum stuff. But when I started making it about me again, I was like, oh, okay, I can feel this. I can understand this. So the hydrogen and helium electrons are roommates, aka orbital mates. Over here, these next two are in the same orbital, up and down. Same here. So you can see here, you have 3 different m sub l values. These are together in the same orbital, same orbital, same orbital. Up, down, up, down, up, down. Up, down, up, down, up, down. And so it continues like that. Up, down, up, down, up, down, up, down, up, down. So I'm going to go ahead and work this out for actual elements. And then when I'm done with that, finishing the last quantum numbers, then we'll go ahead and finish that table I was talking about, right? And that will wrap up today. I think that'll kind of close this out well. Okay, I need a periodic table that actually has elements on it. That looks a little better than, okay, I'll use this one here. This is the best I have today to work with. So I can remember what these are. Let me go ahead with, I'm going to clear this out because I need to write the up down stuff in here. I'll leave the m sub l as 0. I'll write this out here. 1, 2, 3, 4, 5, 6, 7, right? This is up, this is down, up, down, up, down, up, 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 down, 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 up, down, up, down, down, down. Kind of works like that. Up, down, up, down, up, down, up, down. We won't do everything, just the ones I'm trying to label here. Up, down, up, down, up, down, up. This is, of course, down. Up, up, up. Oops, down, down. You get the idea. Up, down, because your roommate's up, down, up, down. Okay, so let's pick a few elements here and we'll write the 4 quantum numbers for these elements. Let me go ahead and highlight which one we're doing. We'll do magnesium. I can't even see what these are. Oh, we'll do oxygen. We'll do bromine, the common ones. We'll do cobalt, platinum, yeah. And then, let's see. Lutetium again, why not? Californium, my favorite. Okay, and then we'll do hydrogen. So this is right here. One, two, three, four. I want to do two in every block, right? S block, two in S block, two in P, two in D, two in F. Okay. So let me start with these right here with hydrogen. So with the S block right here, S block. Now remember the order is N, L, M sub L, M sub S. I'm starting with the element hydrogen. After hydrogen, I'm going to go with magnesium. Okay. So my energy level across for hydrogen, that's going to be energy level 1, right? Because, yeah, this is energy level 1, this is 2, this is 3. And then L, I have a label right here. L is 0. M sub L is not written here, but M sub L is equal to 0 because I only have one column, right? And the M sub L columns are usually 2 columns, make up one M sub L. So that's going to be 0. M sub S, since hydrogen is the first electron and it has an up spin or half up spin, it's going to be positive 1/2. Okay. Oh, while I'm here, let me go ahead and explain this just so I can be clear, right? Remember, hydrogen and helium are roommates, right? So even though I didn't plan to do helium, I'm going to do it right here so we can see. Same order, N sub L, N, L, M sub L, M sub S. Since hydrogen and helium are roommates, helium is essentially right here. Helium energy level 1, L is 0, M sub L also 0. M sub S for helium is the second electron, negative 1/2. You can tell what electrons are roommates by looking at the first 3 quantum numbers. If the first 3 quantum numbers code to the same orbital, then they're roommates. It's like saying, I can tell who lives together by looking at the address. If the address is the same, they must live together, right? The first 3 quantum numbers code to the address of the orbital. So if they are the same, these electrons live together. So hydrogen and helium are orbital mates because the first 3 quantum numbers are the same. This electron came in first, that came in second. Okay? Going on with my charge. Magnesium, 1, 2, 3. Energy level 3. The L, I'm still in L0 because this is the S block. M sub L. M sub L is always 0 for the S block. Magnesium is the second electron, so it's going to be negative 1/2. Okay, so hopefully you're seeing this, right? Goes from, oh my goodness, to a puzzle. This is kind of fun, right? Hopefully, as you're watching me do this crazy thing, you're realizing it's not that awful. Okay, so I'm done with my S block. I did these 3. Now I'm moving on to, I think that's oxygen. It's got a lot of stuff all over it. So once again, since you guys are watching this via video, most of you are, at least feel free. Oh, what just? I'm telling you, this technology stuff. It was supposed to erase and everything just came back. Okay, now we're moving on to the P block. For the P block, remember -1, 0, +1 are my M sub L's. They're all listed there. Okay, for my P block, I'm working on order N, L, M sub L, M sub S. For the element oxygen, and then bromine. Okay, so energy level. P block starts at N is 2. So this right here is N is 2, right? N is 3, N is 4. So here, 2, comma. And then what am I doing next? Oh, L. L for this one should be L is 1. Okay. M sub L. The M sub L is kind of sectioned out like this, right? -1, 0, +1. So this one here is in the 0 section. So that would be 0. Okay, now in the 0 M sub L, the first one is nitrogen, I think, and the second one is oxygen. Let me erase that since I'm now done with all of this stuff. Yeah, first one is nitrogen, second one is oxygen. So oxygen is second, so it has to be -1/2. Okay, now I'm going to bromine. Bromine right here. So bromine, again, these are categorized like that. Bromine, N is 2, N is 3, N is 4, N is 5. Bromine goes with N is 4, right? Comma. L is still 1. Okay, bromine is under the umbrella of M sub L is positive 1. I don't know, there's a lot of stuff written here. So I'm going to say positive 1 M sub L for bromine, right? Positive 1. And then for the electron, bromine is the first one in M sub L positive 1. So it's going to be plus 1/2. Okay, that's it for my P block. Do y'all want me to work on anything extra in the P block? I still have these two to go, right? Okay, I'm going to move over to the D block. D block ones. Okay, for the D block, I'm working with cobalt and platinum, COPT. Okay, remember this is N is 3, N is 4, N is 5, N is 6. So CO3 for my N. And then let's see. I usually need to visualize it. I need to categorize it so I can see them like that, right? Okay, this is D. So -2, -1, 0, +1, +2. So CO is positive. Oh, sorry, I need to do L first, right? L is 2, then it is +1 for M sub L. Then CO is the first electron in the positive one, so +1/2. Okay, so I'm done with that one. Platinum. Oh, platinum is also in M sub L of +1. Okay, let me start from the beginning. Platinum is energy level 5 right here. Platinum is L2. Platinum is also +1. But platinum this time is the second electron, so -1/2. Okay, once you get the hang of this, practice, it's really not that bad. Okay, finally we got these two down here for my F block. Then I'll go ahead and help you guys out with that one question, and then we'll be done. Here, I'm working on LU, lutetium, and then californium. F block. So with LU, let's see. I'm going to break this up in two. Okay. I know this is +3. +2 for my M sub L. Those are the more complex ones. +1, 0, -1, -2, -3. Yeah. Woo! Okay. And then this one here has a L. L is 3. Okay, got that. Now that I labeled it, now I can start answering. For lutetium, N is 4. 4, comma. L is 3. M sub L is +3. Is it the second electron? Yeah, second electron. -1/2. Okay. Then this one here, californium, N is 5. L is 3, same L, because they're all flowers. And then this is +1. And then this part here is CF is the first one, +1/2. And that's it for the quantum numbers. Now, some of the questions they will ask you is, what quantum numbers is erroneous, as in it's fake, it's not going to work. Try to use this chart to find in the periodic table. If you can't find it because the sublevel doesn't exist, or if they give you an energy level of 3 in the F block, you know that's not real, right? So then the quantum numbers are not real, they're fake. Questions like that. So let me go back. There are a couple of slides that I haven't gone over yet, so let me try to write somewhere here. This one here, go over for Wednesday. We did that one already. I'll go over this one too, just to kind of solidify it. and then go over this. But I think the rest of them we're done with, right? And then I'll go over this. The rest of these we are done with. I've done all of this all the way to the end. Okay, so let me do this. Oh, let me slow this down so it doesn't. I'm going to go over the remainder of your lab. This part here. Oh, here you have to do the 4 quantum numbers and they gave you the elements. Oh, that would be fun. We did some of these already. Oh, we talked about that. This is the part I wanted to help you guys with. So what I'm going to do is I'm going to skip over, well, we know we have how many? 4 different L's, right? L is 0, L is 1, L is 2, L is 3. So let me actually do L is 2, okay? So for L is 2, L is 1, this is the S block. This is just a cheat sheet for myself. S, P, D, F. Okay, this is all you need here is the numbers. So let me not be confusing because I feel like if I write more than you guys need, it might be confusing. All you need is just the numbers for here. Okay, this is it. I can recall this. I don't want to be lazy. Okay, when they say write the M sub L for this L, remember M sub L starts with negative L, goes all the way to 0, goes all the way to positive L. So I'll do it for negative, for L is 2. I'll do, this is negative 2, negative 1, 0, positive 1, positive 2. You're probably wondering why I wrote it vertical versus horizontal, right? Because remember, each of these is an orbital. Each M sub L is an orbital. So each M sub L is a room that can handle 2 electrons. So let me write this properly. Negative 2, negative 1, 0, plus 1, plus 2. Okay? So M sub S, for negative 2, we have positive 1/2 and negative 1/2. Assuming that these are full of electrons, positive 1/2, negative 1/2. Each of the orbitals has positive 1/2, negative 1/2. Remember, each of the M sub S's codes to a single electron, negative 1/2. Positive 1/2, negative 1/2. So I should have a total of 10 numbers here, right? 5 are positive 1/2, the other 5 are negative 1/2. Okay? So remember, M sub L has a restriction, positive 1/2, negative 1/2. 1 goes with each of these. So this goes with the top one. Just trying to show you how this goes. This goes with that, and so on and so forth. This goes with this. This goes with that. Sorry, my handwriting is awful because I'm using my mouse. Okay, what type of orbital is this? Here they want the letters. So this goes with this, right? When L is 0, this is called the S orbital. Oh, I'm supposed to be doing this one here. I'm getting too excited. Okay, when L is 2, this is the D orbital. Okay, y'all can fill in the rest. Okay, total number of orbitals of this type. Remember I told you guys that M sub L goes to the specific orbital. So in a way, M sub L goes with this number right here. So 1, 2, 3, 4, 5, or count the pictures in the end of the slide. There's 5 different orbitals, right? Total number of orbitals. They want a number here. So it's going to be 5 different ones. Maximum number of electrons that can occupy these orbitals, or the orbitals. Remember, M sub S, each M sub S codes to a single electron. So the M sub S's I wrote here are representative of the electron. So if you have 2 here, plus 2 here, plus 2 here, plus 2 here, and 2 here, when all these 5 orbitals are full, we end up with 10 electrons. Okay, so you will go through and fill the rest of these. I did number 3 for you. So don't skip. I have people who write plus 1 minus plus 1/2 minus 1/2 here, and then they just stop there, and I'm like, what about the other electrons? Then when they get here, they get the wrong number, because you want to make sure you understand each of these is an orbital. each of these numbers codes to a specific orbital, and that orbital can max out at 2 electrons. So 2 can go here, 2 can go here, 2 can go here, and it all works out. So I've worked number 2 for you. Y'all go ahead and fill in 0, 1, and 3. Okay. We did all this not in order, but we did all of this. So hopefully this helps you guys out fill this. You may not be able to do 7 and 8 yet because I have to start the next chapter, which I will do on Wednesday, so you can finish up 7 and 8. Okay? Okay. I know I've gone on forever, but yeah, this is all I have for today. Do you have any questions? Okay. If not, we shall meet on Wednesday and then complete this chapter. Okay, you're welcome. Have a nice day.